Let's look at the details of the photoelectric effect. Whoops, next page. Next page, next page. There we go. So again, we have a light source which is incident on a metal plate, and that metal plate then will emit electrons which will go across and create a current in the circuit. Okay, so a current, and they're electrons, so actually the official current goes in the opposite direction, but it doesn't matter. There's going to be a current in the circuit. I guess if we want to be really careful, just the current is the direction that positive charges would go. So if negative charges are moving in this direction, electrons, then current officially moves in the other direction. Okay, so that is the photoelectric effect, and then we can do experiments on the photoelectric effect by adding a variable voltage source, which might look something like that. There we go. So that allows us to measure what's called the stopping potential. Okay, so here's remember the issue is that turning up the intensity of the sun. In this case, I'm using the sun, a lamp, whatever. Turning up the intensity does not increase the energy of the electrons. What it does increase, it still increases the current, but increases the current because it increases the number of electrons as we turn up the intensity. But in order to turn up the energy of the electrons, in order to make the electrons go faster, not more of them, in order for them to go faster, we have to turn up the color. What do I mean by turn up the color? We got to go from red to blue. As we go from red to blue or infrared to ultraviolet, as we turn up the light going in the direction red to blue, we get more energetic electrons, which can be measured by the stopping potential. So Einstein was able to explain this by giving light, the color of light, and energy. And he I don't know if we say he copied Planck, but he said that light has an energy which is equal to h times its frequency, right? So, and the frequency is red is lower frequency than blue or ultraviolet, right? So therefore, as we go from RGB, therefore as we go up in frequency, as frequency is increased, therefore energy of light is increased. And that's how we understand it today. But that was not understood, and that's what Einstein proposed to explain the photoelectric effect. And it explained it fully. Let's see how. So Einstein suggested that light comes in these quantized packets of energy, which are equal to hf, and each of those quantized packets is called a photon. So here's the explanation of the photoelectric effect. Quantized packets of light energy called a photon, each has E equals hf. Now what you need to think of here is, in order to understand this, is that this light here is balls of light, right? It's like particles. So here, let me draw it as a different color. There are particles instead, and each of those particles has energy hf. That's a photon. A photon is a particle of light. A quantized packet of light is a particle of light. Each of those has energy hf, and I'm just going to jump ahead. The more of those that you have, you get more by turning up the intensity. You get more of them by turning up the intensity. So you get more of those, and that's why you release more electrons, but not more energetic electrons. In order to increase the energy of them, you have to increase the color of the light. All right, now let's see. Let's go ahead and explain that. So this is Einstein's explanation of photoelectric effect. First, light comes in packets, E equals hf. Second thing, which I didn't show in the demonstration, that Einstein explained, is that a certain energy is required to get any photocurrent, any electrons going across that gap, independent of the intensity of the light. So no electrons are released if you use light below a certain frequency. That frequency is called the cutoff frequency, or F0. So therefore there's a cutoff energy, E0 equals HF0, below which no photocurrent will travel. And that's explained by the fact that there's got to be a certain release energy for a given metal. And it turns out that this was material dependent. So this is material dependent, the cutoff frequency. And that's explained by saying there's a certain amount of energy, and we call it Greek letter phi, which is the work function. And that's an energy. The work function is an energy, and it's the amount of energy it takes to release electrons from the metal. and that is equal to HF0. Oops, that's work function, and that's equal to HF0. That's the threshold energy, also called a threshold frequency or cutoff frequency. That's the threshold energy below which you get no electrons, above which you start to get electrons. Using the adjustable potential difference in the photoelectric effect, you can then measure the kinetic energy of the electrons, or the maximum kinetic energy of the electrons, because they all come off with a slightly different energy because it's a real experiment. That's K max. You can measure the maximum kinetic energy is equal to HF minus phi. In other words, or we can write that as HF minus HF0. In other words, now we're saying that light that is releasing electrons has a certain energy HF. If you subtract the amount of energy it takes to release them from the metal, the rest of the energy goes into the kinetic energy of the electrons, which is now measured in this experiment. We're measuring the kinetic energy by measuring the stopping potential. And that stopping potential, therefore, right, we can do the experiment to show that once we stop it, EVS, where VS is E is the charge of an electron, VS is the potential. Turn up the voltage enough, we get no photocurrent, and we know, therefore, we have now measured the kinetic energy of those electrons coming off of the metal. Or we put these few little factoids together just to have an equation which is sort of describes some part of the photoelectric effect, if you like, which is that. We can measure the stopping potential. We know because of J.J. Thomson's work soon before this, the charge of the electron. We know H is Planck's constant, the frequency of the light, and the stopping potential. So if I'm sorry, not the stopping potential, this is the work function of the metal, how much energy it takes to release an electron. So if we can measure, any two of these things and determine the third. Again, the work function of the metal is HF0, where F0 is that threshold or cutoff frequency. And also, if we might talk about cutoff wavelength or wavelength, and remember that wavelength and frequency are inversely proportional by the speed of light. C equals F lambda.